Wait, good.
Still practice problem number 4. We used a chart to figure out that at 27 Celsius, the partial pressure of the water vapor will be 26.7 torr. And then Sarah told us that we need to subtract. So basically total pressure is just the pressure of every single gas, however many there are, added up. When we solve for the pressure of just the carbon dioxide, what do we get, Sarah?
You get 7.60 times 10 to the second floor.
Okay. Now, do you understand the significant figures that go with that? So, significant figures, usually we do it when we're multiplying and dividing. When we're adding and subtracting with significant figures, you've got 787 minus 26.7. Now, you don't just say this is 3, we'll keep 3, like you do when you multiply and divide. In this case, you actually have to say I have significance in the ones place in both, but only the tens place in this one, not this one. So I can't keep the tens place. I have to round to the ones place because that's the place where both of them have significance. So this would be like 0.3, right? So then I have to round to the ones place. But if I had written 760 torr, that would not be significant in the ones place unless I either underlined it, put a decimal point, or used scientific notation. So Sarah used scientific notation to show 3 significant figures ending in the ones place when you subtract like that. Okay? So adding and subtracting adds a whole new level of fun to significant figures. But there you have it. So number 5, Amy. Alright, what do we have on number 5? As part of an environmental experiment, a mixture of gases released from a smokestack is collected in a balloon. And then the mixture is analyzed and found to have 15 grams of, what is that, SO2?
That thing that was actually
sulfur dioxide.
Yeah.
There you go. It's covalent, so you have to name it with the prefixes, sulfur dioxide. 12.1 grams of NO, what is that? It's covalent again, so.
I don't know.
What's N?
Nitrogen monoxide.
Monoxide. Nitrogen monoxide and 2.5 grams of SO3. Sulfur trioxide. Now we're back to covalents. We've forgotten about them, haven't we? What is the mole fraction of each component in the mixture? Okay, so
Oh, I hated this one.
what did you do to find the mole fraction? Well, first you have to find the molar mass of each of them. Because obviously to find the mole fraction, we need to find how many moles of each, right? And we have grams of each, so we need moles of each. So we'll do molar mass. We want to cancel grams and get moles. I should have left more space. So how many grams are in a mole of sulfur dioxide? Well, like get up
4.1.
Oh, good, you know. And nitrogen monoxide
30.0.
and sulfur trioxide 80.1. So then,
Clay, can you please stop playing with the camera?
when we convert to moles, how many moles of sulfur dioxide do we have?
0.234.
And she kept 3, which is appropriate moles of SO2. You always have to write the chemical or it gets too confusing. And how about nitrogen monoxide?
0.403.
Moles of NO. And sulfur trioxide
0.039.
SO3. So now we have moles of each. Well, now how am I going to figure out mole fractions?
You have to add all of those together.
Add all 3 of them up. Okay. So we'll add the thousands place, and they're all significant to the thousands place, so that's convenient. If they weren't, we'd have a significant figure disaster. 3 plus 0 plus 3 is 6. 2 plus 4 plus 0 is 6. So I find the total number of moles of gas to be 0.668. Is that what you found?
Yeah.
Okay. Then what do we do to figure out?
Then you have those divided by something else.
Divide something by something and we'll get it. And what would that something be?
Oh, the answer is divided by that. The
Okay.
total.
So for SO2, if I did 0.234 moles SO2 divided by 0.668 moles of total gas, what would I get?
0.350.
I'll check 1.3. Okay. Right. 350, is that what you got? And how about units for mole fractions? What do you think about units?
Oh, it's it doesn't have any.
Yes, these are unit lists, so you guys can't get docked for, disastrous units. So the mole fraction, but you do need to make sure you
Praise the
tell
Lord.
me, yes, which chemical is, going with which mole fraction. So, how about nitrogen monoxide? We're just going to divide its number by that, and what do we get?
0.603.
And sulfur trioxide?
0.046.
Okay, all unit lists. It's one of those moments I can't tell you to put units. So just make sure you've labeled them somehow. I can tell what you're doing. So those are mole fractions, hooray. So I'm on Heather, and I'm on number 6. If the total pressure of a gas mixture from the problem above, which I'm glad I didn't erase, is 1.1 atmosphere, what's the partial pressure of each gas? So we'll trade colors. We know that the pressure is 1.1 atmospheres. So we'll move everything down so I can stand here. So do you know the equation for partial pressures that stems out of Dalton's law of partial pressures?
Can you just put it on the table and leave it?
No, you can't. I have to hold it. You're gonna see the board.
Numbers up there.
Right, so you're going to use the mole fractions of each of the gases in the mixture to find the partial pressure. If you know total pressure is 1.1 atmospheres, is that 2 significant figures? Yeah, okay. So how do you find partial pressure? Easy equation.
What?
So pressure is going to be the mole fraction, which we'll call X, times the pressure of the component, I guess. Which I guess I could just label here SO2 or NO or SO3. So if you just multiply the mole fraction times the pressure, you get the partial pressure of that gas. So the partial pressure of SO2 is, I wrote that wrong, SO2 here is going to be the mole fraction times the total pressure. So for SO2, that times pressure, and what would you find that to be?
0.39.
And she kept 2 significant figures because this is 2, that's 3, so you have to keep 2. And what unit would you have? ATM, atmospheres. So for SO2, it would be 0.39 atmospheres.
Automatic teller machine.
How about NO?
0.66 ATM.
Do you know how funny that joke is?
And sulfur trioxide.
0.051 ATM.
So when you get them all, you want to add them up
Always
and make
do.
sure that they
Always
add up to what you know the total pressure to be. So if I added this up, I'd get 9 plus 6 plus 1 is 16. And 5 plus 6 plus 3, 11 plus 3 is 14, 15. I would get 1.56 atmospheres, so I would start to worry because I don't get
Always tell
1.1
Mom.
atmospheres there. So I'm thinking we got a mistake somewhere, so then I'd go digging for it. But
Well,
the sum, Dalton's law says the sum of the partial pressures has to equal the total pressure. So we got, is this 0?
yeah, I
Point
got
zero.
0.05.
Okay, that makes sense then. So then if I added them up, 0.39 plus 0.66 plus 0.051, then I get 1.1, and then we're all set. 1.1 atmospheres of total. So the answer would be this, this, and this, but if the sum of the pressures doesn't add back up to that, you've got trouble. And that's a good way to check. Make sure that you think through your work and say, does this make sense?
No, it always makes sense.
All that's saying is if I pump
I don't
3
either, so don't worry
gases
about
in
it.
here, just pump 3 gases in here.
Play.
I measure the pressure and it's 1.1 atmospheres, like if I had lab equipment, and I could measure the pressure, it'd be 1.1 atmospheres, right? Then I would know that if I put in that much sulfur dioxide, that much nitrogen monoxide, and that much sulfur trioxide, and I had a total of 1.1 atmospheres, I could tell that the partial pressure of each gas just adds right up to the total pressure. I mean, gases don't behave differently based on what they are. They all behave the same as each other pressure-wise. So you don't have to kind of worry about, oh, this gas will have more pressure than that gas, because that isn't how it works. So we're on 7, Michael? Let me erase all this. Okay, so Michael.
Can I go use the bathroom, please?
Sure. A steel container is filled with 5 atmospheres of nitrogen, Michael, 2 atmospheres of oxygen, and half an atmosphere of argon. What's the total pressure in the vessel and the mole fraction of each gas? So, what do you know about all 3 of those gases that might make a difference at some point here? Actually, just 2 of them. 2 of them are homonuclear diatomics. So, let's see, we're on 7. So we have 5.00 atmospheres of nitrogen gas, and we need to write that as N2 because you know nitrogen gas is a homonuclear diatomic. 2.00 atmospheres of oxygen gas, and half an atmosphere of argon. So, what is the total pressure in the vessel? Super easy. When you add 3 gases, total pressure is just the sum of all the partial pressures. Yep, that's it. So, and they all go out to the hundredths place, so we can do 7.50 atmospheres total pressure. Okay, so that's easy. Then, what's the mole fraction of each? So we just use that same equation that the pressure of, say, one gas, like nitrogen, is going to equal the pressure of the total times the, what's that thingy called, the mole fraction. So, in the last case, we knew the total pressure and we knew the mole fraction. In this case, we knew the partial pressure and the total pressure, so we can find the mole fraction that way. So, pretty easy. 5
Excuse yourself.
atmospheres
I'm not excusing
of
myself.
nitrogen equals total.
What's your shirt, the Joker?
Yeah. I gotta
And
do
then
it.
the x
I
is
love
the
it.
mole fraction. So how do I find that mole fraction?
Is it one of those ones that's like ask about the Joker, they'd be like, no, dude, are you not looking at it? It's the Joker
And what do I
suit.
get?
That's all it is. Just him going like that.
0.6.
That's not really sure. There's like a face.
Okay,
The
so we'll
sides are-
round to 3, because that has 3, that has 3. When we multiply and divide, we can keep 3. And how about units? What did Amy say?
What did Amy
I don't
say?
know what I said.
Why do I need it?
About the units of a mole fraction?
There isn't
Any.
Right.
Oh,
The Heather
I
knows.
said that.
So mole fractions
Good
are
job.
unitless.
You
So
know,
then, if we just divide each of these guys by the total pressure, then what's the mole fraction of oxygen? So oxygen's pressure divided by the total to 3 significant figures. 2 divided by the total pressure for oxygen.
2.9.
0 point,
Wait, what?
well, 2 divided by 7.5 will be some sort of fraction. Mole fractions are always less than.
It's a struggle, yeah.
.267. Is that how far you're going over?
And X of argon, so 0.5 divided by the total pressure. And we,
0.7.
What problem are we on?
I don't know.
and how many significant figures can I keep on this?
Yeah, we're on
7.
So
Hey, I got some.
0.75. Okay, so now, no, that's not what I got. 0.5 divided by 7.5.
7.
I got .067.
Yeah.
Okay. Yeah,
That's
yeah,
what I
that
got
did
too.
work. 0, 6, and actually, yeah, that's right, 067, that works. Because that's 2 significant figures. All right, Josh. All
I
right.
don't know, can you?
So that's all. Actually, that's the whole problem.
You got told trying to tell
just
him.
using this equation, kind of the opposite. All right, now we'll get into the harder stuff.
Oh, great.
Who am I on? Sterling.
Okay.
No.
Oh shit, I got rid of both of them.
Color. So Sterling, what is the volume of 16 grams of chlorine gas at 1 atmosphere, 25
You
Celsius?
just want the answer of the
No, I want the whole problem.
What?
16.1 over 1 times 1 mole over 71.
You can write down the equation if you can.
And why did Sterling use 71 instead of 35.5?
It's right there.
the 2
Because chlorine's homonuclear diatomic. When you get its molar mass, you have to remember that. He's not telling you
There's
those
2 of
things
them.
anymore. Okay, so then what do I get? Sterling?
0.227 moles.
1 mole of H2O2.
Alright, so we found moles first. What's our goal?
To find the
Volume. Okay.
Over
then I have
grams of
that
34
so it's volume equals nRT over T
They cross
equals
So this is the combined gas law. PV equals nRT.
and that's equals
Rearrange to solve for
over 7
volume.
moles of H2O.
0.227 times 0.821 times
Hold
290.
on, give me units.
So you can cross out.
Okay.
0.0821
And then that equals 50.
Oh, that's
moles
the
of
portable
H2O.
unit. That's R.
and then 0.298, which is I believe the color. And then
That can't be. Hold on. Give me half a
It
second.
can't be.
298, not 0.298.
oh, did I say point?
Or maybe I just heard.
298. And then it's
And
over
so then you
1.
plug that into this equation,
Over-
which is the one.
Oh, because it's 1 atmosphere.
So it's going to be V
Is that 3
equals
significant figures with 1?
50.4 moles
Okay, so what do we get?
5.5.
times 0.
What's the unit on R?
5.5.
Oh, slow down, slow down.
Hold on.
5.5.
0 or times 0.0821.
Okay.
And It's gonna be.
So the units on
liters
R, in
times
physics we use a
ATM
different R
over-
because we don't use liters and atmospheres. It's the same
over,
R, it's just converted to
moles
different
times K.
units, so that's confusing. Alright, so Sterling, when you type all that into your calculator, what do you?
Five.
Then you're gonna have times 810
5.55, what?
liters.
Liters for volume, and that's probably what I got.
I'm actually in trouble deciphering my own writings right
Wow,
now.
your papers are
Equally
Yes.
over
You just
1.2.
type them all up and.
I did have a new one of this, but somehow it got lost. So this is my super old one. Okay, so then let's think that through.
1.2 ATM.
Okay,
So then you get to cancel.
alright, so 5.5 liters of gas. Do you guys know what a 2-liter bottle looks like?
Yeah.
soda bottle.
Okay, so think through. 16 grams of chlorine gas. 16 grams, how much is that?
It's a lot.
16 grams? Like the mass of this is 100 grams of just like not the whole container, but just what's inside, 100 grams. Okay, 16 grams is like a tiny amount, like 2 ice cubes or something. Okay, it takes
I don't know, it's kinda
5.55 liters, so like 2.5, 2-liter bottles. So tiny amount of chlorine gas fills that at kind of basically room temperature in 1 atmosphere. So like tiny bit of chlorine gas takes up huge amount of space.
Here we go.
Thinking through what that really looks like, what it really means. Also, please note that Sterling was given 25 Celsius and he immediately converted to Kelvin because you cannot use Celsius in gas laws. For one thing, it won't cancel your units in R because R has a Kelvin unit. Celsius doesn't cancel that. And for another thing, you could end up with a 0 in the denominator because remember with Charles' law, or any of the gas laws, if you use Celsius, you can have 0 degrees Celsius. Putting a 0 in the denominator gives you an undefined number. Clearly that's bad. So make sure that all gas problems have Kelvin instead of Celsius. 9 is Josh. Oh, this is a fun problem. Silver tarnishes in the presence of oxygen and hydrogen sulfide according to the following equation. So, 4 silvers, which is solid of course,
It's snowing.
plus hydrogen sulfide.
Well, I guess we get out of school today. Wait.
Yeah, I
You
did.
even looked out the window, you put your
It
arm.
wasn't snowing when we went it.
Yes,
it was.
It's been snowing for like
Oh,
50
plus
years.
oxygen.
The camera.
Okay, where is silver sulfide?
Yeah, drivers. Because of the rubber, it's like gripping to the table and then sticking on and just keep on going down.
I think Clay's being lame and just pushing me.
Oh no, that's a solid.
Those
Alright,
fancy
so
cameras.
tell me one thing here.
Vibrating camera.
Alright, super focused. Why does it matter what my phases are? Why do I have to really watch solid, gas, or if there were aqueous, which there isn't? Why does that matter at this point? Right, this is gas laws. We can only use those things which are gases in the equations like PV equals nRT, right? So you
So-
have to,
If like we're like trying to solve this, what you're saying is if it's a solid, you can't. It
you
doesn't
can't just
really
plug
have
it
any
into PV
relevance.
equals nRT to find its volume. No, that only works for gases. So make sure that you're using, the right equation. If you want to find the volume of a solid, you have to like measure its sides and use a volume equation. If you want to find the volume of gas, you can use the gas laws. So poor Josh is still waiting. Usually hydrogen sulfide is the limiting reactant, which kind of makes sense because if you have a big chunk of silver, there's lots of it, and there's tons of oxygen in the air. So usually hydrogen sulfide is not a big component of the air, so it's the limiting reactant. So all your math is done with the limiting reactant. You always have to use the limiting reactant. If you use an excess reactant, then your math won't work out because the limiting reactant runs out before the excess reactant is right. If a silver spoon is put in a container with 56.7 milliliters of hydrogen sulfide, at 1.23 atmospheres, so a little bit of pressure there, 22 Celsius, which is what, Josh?
975.
Oh, it's 295.
295 Kelvin. 975 Kelvin would be something else.
Kill the
Maybe
world.
a silver smelting furnace or something, but
That'd be nice right now.
no, we'd be dead. How many grams of silver are we going to make? So our goal here is grams of silver, which is kind of nice to keep in mind because, you know, all of this can get kind of confusing at times. So where do you want to start?
You have to figure out moles of silver. Oh wait, yeah, you have to, because you want to get grams of silver. So you have to figure out moles, and you don't use that equation PV equals MRT. You have to figure it out for N. N equals PV.
Okay, I'm good with that because the H2S
Fly
is a
away,
gas.
Stanley.
So look, Josh is going to start out with his limiting reactant, which is a good choice. He knows it's a gas, so if he wants to find moles of it, he can use PV equals MRT. So
PV equals nerd.
we want to find N, which is moles. Don't forget N is moles, which doesn't seem right.
Equals nerd.
So pressure, we know pressure. Do we know volume?
Equals nerd.
Yeah, because 0. Well, it's 0.0567.
Yes, 0.0567 liters. Good. And that's H2S. PV equals N, which is what we want, times R, which we know is at 0.821 per mole Kelvin times 295.
Yep.
Whoa,
Okay.
you did that like a boss.
Whew, barely. Okay, so if he does this times that, divided by R, divided by temperature, what will he get for N? Josh, what'd you get?
0.00288 moles.
And looks like he's got 3 significant figures for everything, so that's good, and that's of H2S. Always keep the chemical in your math. Very, very important to tell me what chemical. Because what's your goal? Grams of silver. What do you have? Moles of hydrogen sulfide. So we're not there yet, right? So how are we going to find grams of silver now?
You have
So
to convert to, you use the mole ratio. So you go times 0.00288 times 4 moles of Ag over 2 moles of H2S.
okay, so he's using stoichiometry from the balanced equation. He wants to convert from moles of hydrogen sulfide. Cancel those out because there are 2 of them. 2 moles of silver, 4 of them. So then, what do you find?
0.00576.
576. And that's moles of silver.
Yep.
Okay. So then, we got moles of silver. We want grams of silver. What do we do?
You have to find the ratio, and it's 0.00576, and then there's 107.9 grams. Yeah, 107.9 grams in the mole.
Ag per 1 mole of silver. So we multiply that tiny number by the molar mass of silver, and we get
0.622 grams.
all right. So is that what I got? Yep. Got 3 significant figures, which is perfect. You have number, you have unit, you have chemical, and a complete answer. That's all good. Anyone have any questions about that? Because I know sometimes we struggle with stoichiometry. Just, yeah, just keep in mind that you have to practice. There are extra practice problems in the back of the book. Practice them. Your parents can show you the answers when you're done. Start with your limiting reactant. Josh started right here with what he knew about the limiting reactant. He knew it was a gas, so he could use a gas equation. And then just keep in mind, what's my goal? How can I use the balance equation? How can I use the molar masses to help me get to my goal? So that's a big problem, but 10 is kind of even more fun.
He's trying to get we're trying to get a shot of the answer, but you keep walking in front of it.
So like, it's just funny because he keeps like zooming in every time you leave, and then all of a sudden you walk back around it, so he's just
It's
like
0.622
cameras
grams of
in
silver.
going.
They're gonna be sitting there like, oh.
And probably our
Be like
audience-
spitting.
I do plenty of pausing when you're watching this video. Just saying.
So the last problem is Clay's. Oh good, a rocket engine using
What happened?
peroxide.
I did the problem.
So Clay's got a rocket engine that uses aqueous hydrogen peroxide. Anyone ever done that? Use peroxide to shoot up a rocket?
Wait, hydrogen peroxide.
Oh, is that like when you put like the Tums in it and it goes?
No, that'd be like
Are you thinking of Mentos?
Mentos
no.
and Diet
What-
Coke you could do.
What's the peroxide thing?
Peroxide
This
helps cleanse
has
out your
what
wounds.
dinitrogen.
Oh, what a relief it is.
Like, do you light it on fire, or what do you? How do you make it?
It's a chemical
Propel.
reaction. It gets hot. Probably this wouldn't be like what you use for home hobbyist rockets. N2H4.
Man.
What's N2H4? Is that gas?
I just popped my knee. Good job.
And then we produce nitric acid. Definitely not the home scientist version of rockets here.
Man.
Maybe he's a terrorist.
That's a
I actually asked if we had ever done this before.
waters.
It's like, what if you had said yes?
Yes.
Well, there may be other rockets that use peroxide. So Clay, give that to Daniel and help me with this problem. So,
I got the dude. What's your problem?
That's Zoom. That's Zoom.
I know what Zoom is. I played with it while you were gone.
now Clay.
Wrong button.
Listen. Focus, Michael.
I can tell.
Clay.
Yes.
It says if the rocket engine has 1,500.0 grams of peroxide and an excess of N2H4, then what's the volume of water? So if N2H4 is in excess, what's the limiting reactant?
The limiting reactant is the hydrogen.
Right. So if this is the excess reactant, there's only one other reactant. It's clearly the limiting reactant, so you know to use that one for the math. And it gives you information about that one. If it gave you information about two reactants, but it told you which one's the limiting one, only use the limiting one. So what volume of water vapor? So our goal here is volume of H2O vapor. All right, this. Is that, why does that say aqueous? This should be a gas. All right. What volume of water vapor is produced when the rocket gets to a temperature of 540 Celsius? So Clay, what's the problem with 540 degrees Celsius when we have gas laws?
What do you mean? Oh, you have to make it Kelvin.
Make it Kelvin. So what would that be?
I don't know. I'm not sure. I can't compare this to the end. Damn, what do you have?
I don't know.
I don't know.
Well, how do you convert Celsius to Kelvin?
Dude, what you?
It's not long enough.
Somebody like.
I'm not even sure how I got my answer
Michael, how do we
anymore.
convert Celsius to Kelvin?
I question my own existence.
Because you're talking.
Because he doesn't know.
Wait,
Hold on, Michael. How do we convert Celsius to Kelvin?
That's a lie, Leah.
Use a unit conversion.
Oh, you add.
no, I thought you subtracted.
Go ahead.
You added subtract.
I thought you divided.
Right, so you're gonna add because Kelvin will never go all the way to 0. It's always gonna be bigger than Celsius. Celsius can go to 0, Kelvin can't.
So wait, you just add 200. You just add that, and that's
Yeah.
conversion.
Yeah.
That's lame.
So
I was expecting
Frank, what do
some
we get
big
for Kelvin
equation.
temperature?
So then you'll get 800. Let's see, 13.
And where do I round that? If I look in the book, how many, is there significance here?
Yeah, that's a significant figure.
If you have this number, unless there's a decimal point or it's written as 5.40 times 10 to the 2, This is two significant figures. Okay?
Okay.
So just 540 means that you don't have significance here in the ones place, so we're going to have to round here. So this should really be 810 Kelvin. I think in the answer key, he might have done that wrong. I think he used 813 Kelvin. But technically you should round that to 810 Kelvin. I'm not going to be too fussy about that. But we'll use 810 because I'm pretty sure he was wrong in the answer key.
Don't pull the...
Because this is not a significant figure. So, now, what's our goal? Volume of water vapor. What's our limiting reactant? That. And the pressure of 1.2 atmospheres. So how can I find, if I have grams of my limiting reactant, then how can I get to a place where I can convert from it to the water vapor? What do I need to know?
You need moles.
I need moles. So I'm okay with that.
It's on your papers.
See? I like that. Yep. Alright, so let's convert to moles of water vapor. So, how would I convert that?
1,500 grams of H2O times 1 mole.
This is peroxide, H2O2.
Oh, my bad.
Damn, no.
I'm sorry.
1 mole of H2O2 over 34.0 grams of H2O2.
Okay, so I cancel my grams, I got moles of peroxide. How do I go from moles of peroxide to moles of water vapor?
Then you go times 8 moles of H2O over 7 moles of H2O2.
Alright, so that cancels moles of peroxide, gives me moles of water vapor. So that's good. Then what do I actually get there?
50.4 moles of water.
Okay, so that's a lot of significant figures. That's 3, keep 3, that works. Okay, so now that I know moles of water vapor, how can I find volume of water vapor?
You go 50.4 moles of H2O.
Well, what equation am I going to use? Keep it clean.
V equals,
What equation do you use for gas laws? Because that's a gas.
V equals N times R times K divided by P.
N R T maybe?
Oh, yeah.
Oh, sorry.
Divided by P.
I just jumped to the Kelvin thing. I'm sorry.
Oh, temperature in Kelvin. Very good.
I'm sorry.
No, that's good. Alright, so moles, 50.4 moles of water. And then times R, which is what?
0.0821.
0.821 unit.
Liter L over ATM over moles over K. Or moles times K.
Okay, so liter atmosphere per mole degree Kelvin. So that mole, of course, cancels with that mole. Temperature. Did you use 813 or 810?
810.
And that Kelvin cancels there. Room.
Over 1.2 ATM.
1.2 ATM, so that cancels the atmospheres. So what's my unit that's left?
Liters.
Liters. So volume equals
2.8 times 10 to the third liters.
two significant figures. 2.8 times 10 to the third liters of what?
Of H2O.
Of H2O, water vapor. Is that what I got?
Keep notes while like filming at the same
Yes.
time as not. Oh, hey, look, that works.
Okay. So, 2.8 times 10 to the third.
No,
It's on the camera. 1, 2, 3. So 2,800 liters of water vapor. Do you guys know how much that is?
A lot.
2,800 liters of water vapor.
That's like a lot of soda.
Yeah, well, it's a lot of
Water.
boiling hot steam.
It's not that much soda for me.
So, you know,
Just one.
gushing out from under the rocket. So that would be a stay back kind of moment.
Really?
How much shall we review? How much time do we have? You can stop the camera now. 5 minutes.